Hello everyone, good evening, and welcome to the OneClass channel. My name is Fejiro, and I'm an Honors Bachelor of Science graduate working towards medical school at the moment. Today we're going over some commonly asked chemistry questions at both the high school and college levels, okay? So if you need some homework help or extra tutoring, please check out the links in the description below. And with that, let's kick it off with our first question for this session. And we are going to be solving this. Okay, give me a quick second just to make sure. So we have, sorry, there we go, there. Write the complete ground state electron configuration for scandium, okay, atom. And then B, it's asking us for noble gas shorthand notation. All right, so how do we approach this question? Well, for this, it's always important to just go through our electron configuration rules, which is of how we start. We have 1s, which is going to be for the first row. This is going to be for the second row. The third row will have, well, not technically third row, but the third shell. These are all the possible combinations. And the fourth shell will have, and then the fifth shell, and so on. But because scandium is relatively early, it is a 21st element, we won't have to go that far. So with that being said, let's actually cross 2 to see how far we go. So in each s orbital, it can fit only 2 electrons. P orbital, that's 6 electrons. D is 10 and F is 14. So considering that we're starting from hydrogen and helium, we're counting through the periodic table, okay? We only have this filled out so far. So we have 1s2 because those are filled, okay? And then we move on to lithium, beryllium. That would also be our S shell. The S shell is a first and second column, including helium. And the P shell, as we're going to see, is going to be the columns 13 through 18, not including helium, okay? So now we have 2s2 for the lithium, beryllium. And that means from boron through neon, that would be 2p6. And then for sodium to magnesium, we now have 3s2 completed. And then from aluminum to argon, that would be 3p6. And then we move on now from potassium to calcium, that is 4s2. So now we've done all these. And the scandium, okay, is going to be the 21st element, as we said, and it's going to be touching the d orbital. So we're actually going to circle it as a way of signifying that is where we're leaving off. We have a 3d1. Okay, that's for scandium. And for the sake of reorganizing it to keep all the threes or all the orders, the numbers that come in front, the coefficients, we want them to all be going the same order. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. Okay, so this is what we have for scandium, I believe. Yep, that's the element we're dealing with. Okay, so now for the noble gas notation. As we mentioned, all the way to argon, okay, if we were to get the element of argon, we would be stopping at 3p6. So all of this will be the notation for argon. The goal of the noble gas notation is to pretty much, we start from the most recent noble gas and then we work our way back up. So the most recent gas is argon. So we would write it like this, okay? And then we would go back to counting as normal, and we saw that there was a 3D1 for S2. This right here would be our noble gas shorthand for scandium, because you see argon, that's where we were, and then we fill in the rest. And you actually notice that if we counted every superscript, we would actually end up with 21, because that's the 21st element. So we have 1s2, right? So 2 plus 2 plus 6, so that's 10, then 12, then 18, 19, 20, 21. Thus confirmed this is indeed our 21st element. And you'll notice that argon, the 18th element, we have 2, 4, 10, 12, 18. There we go. We used the 18th element, and then we added 19, 20, 21. And that's how we got scandium. So let's see how we did. So exactly, 1s2, 2s, and then it keeps going to 3d1. And, oh, whoops, write the electron configuration of iron. So we did not finish solving this. So we have the noble gas configuration for scandium. So let's actually see what iron would be. So iron is right here, okay? The 26th. So instead of at least we solved here, and because we're going to keep it relatively short, we're still going to start with argon, because that is our most recent noble gas. But instead of it being 3d1, we actually have 3d2, 3, 4, 5, 6 on the iron. So it'd be 3d6 and then 4s2. Okay. Personally, I like to write with the coefficient lowest to greatest. Some people just write whichever one is coming up, as in which orbital you're in. But that's how I personally like to write it. But this would be for iron. Okay. So we have a scandium here. Okay. And as the question was asking, this is for iron. So scandium, yep, we have that. And then iron, this is the longhand notation for S2 3d6, which is what we have at the moment. And then they replace it with argon, and so they have argon for S2 3d6. As I said, I like to keep it with the lowest coefficient first. That's why I have 3d6 for S2. Because that's also how the orbitals will align themselves. It is technically in the third orbital, so it would come technically prior to the fourth orbital, even though it is in the D shell. So this is correct nonetheless. Let's now move on to question number 2. How do you calculate molarity from molality? The reason why, because I have read over this question and it was just a typo there. What they meant to ask was molarity from molality. Okay, and a difference right now, we're actually just going to focus straight for units. Okay, molarity is moles per volume. Okay, that is the big M molarity. Okay, and molality is small m, but it's going to be grams of solute over, or kilograms of solute over kilograms of solvent. So think of it as molarity is using the moles per volume, and molality is just working in terms of like I guess the, whoops, sorry, this would not be it. It would be, so the volume stays the same, but this would also say moles. So this is N still. So we still have the moles for each one, hence the name mole. But in terms of the N, the molarity versus molality, molarity deals with volumes and molality deals with mass. Okay, so that's a key difference there. So to convert between each one, you have to make sure that you have the right components. So with that being said, if you wanted to get moles per liter, for example, into moles per kilogram, you'd have to, have it set up where you have right now the molarity, you have to multiply by that volume, but then you'd also have to divide by the kilograms, okay? And then these would cancel out, these units, leaving you with the molarity. Now, there's actually a cool thing here. This component here, if you flipped it over, it would actually look a lot more familiar. So kg, grams per volume, okay, that's also known as density, okay? Density, P, is equal to mass over volume. So what we did here, actually, to go from molarity to molality, we divided by density, because when you divide now by density, you now have the volume in the numerator and the mass in the denominator. So in summary, based on all this, to go from molarity M to molality, which is a small m, you actually divide by density. And then you probably guess if you want to go the other way, it would be molality times the density to get the molarity, the bigger m. Okay? So that is a little cool trick there. And then exactly, you see they're giving us the density, and then what they did here is that they got their moles, they have their mass, and then they were able to they have to compute the mass of the solvent, and so that is what they have there. And through this, just to make sure, 1 kilogram, 1,000, they have 0.944 kilograms of solvent. So it's 3 moles per 0.944 kilograms of solvent, and they got their molarity. I mean molality, not molarity. Okay, so they initially started with 3 moles of NaCl, so 3 moles per liter, and then they were able to find their density, 1,120 grams over, well, just to make sure here, minus 175 divided by 1,000. That is what we got there. And so the molarity and the molality aren't too different. You just have to make sure they remember that you want to be using the volume of the solution and the kilograms of the solvent, okay? Those are specific because if you're then going to be using the density, you want the density of the solvent, not the solutes. Well, the solution overall, you want that density. You don't want to be using the wrong density, because then that would hurt the conversion here. But yes, so this would be how you'd work from molarity to molality. It's just important that you take notice of your units, and that way you will not get lost with this question. Okay, so now with that being said, let's now move on to question 3. Okay, so we have temperature difference on the Rankine scale are identical to differences on the Fahrenheit scale. Okay, so Rankine scale, let's just say R, is equal to the difference in the Fahrenheit. So the change in Rankine is the change in Fahrenheit, is what they're saying there. So if Fahrenheit were to increase by 1 degree, Rankine also increases, or Rankine also increases by 1 degree. But absolute zero, okay, so absolute zero is known as 0 Kelvin, is also equal to 0 Rankine, okay? So this is what they're giving us here, okay? And we know that 0 Kelvin, okay, is also known as, because 0 degrees Celsius is 273.15 Kelvin, so 0 Kelvin is equal to, okay, -273.15 degrees Celsius, okay? And now we want to find relationship between TF and TR, okay? And then B, find relationship between TR and TK. Okay, so what we have here so far, all right, based on this information, is that zero Rankine is also equal to negative 273.15 degrees Celsius. Okay, so with that being said, how much does zero Rankine equal for Fahrenheit? That's what we're trying to find out here. Okay, so because we want to find the TF and TR, so what we're going to do here is use the unit converter here. Hopefully it has from Celsius to Fahrenheit, and we're going to use that to convert these Celsius to Fahrenheit and see what we get. So I think it's one of these that I keep my constants. Units of energy, units of pressure, grams. Oh, this is unfortunate. Well, nonetheless, I will keep this page. Now we're just going to actually, for our sake here, oh, wait, is this? No, this is not it here. Okay, no worries. Celsius to Fahrenheit formula. There we go. And here, wow, Google's gotten really advanced. So we have 0 Celsius, or I guess any Celsius, x Celsius, times 9/5. So like some degree, x plus 32 is equal to the degrees in Fahrenheit. So we're going to get that negative 273.15 times 9/5 plus 32. So we have, in this case, 0 Rankine is equal to negative 459.67 degrees Fahrenheit. Okay, and now here's a cool part. We established here that the change in Rankine, change in Fahrenheit is equal to the change in Fahrenheit. So the relationship here is that, I guess if we put in y is equal to x, actually, that's what we can put. Y, which would be the Rankine degrees, is negative 4. Well, we put the x first. So y degrees in Rankine is going to be equal to x degrees in Fahrenheit minus 459.67 degrees Fahrenheit. This is going to be the conversion between the Rankine and Fahrenheit, because we established that Rankine 0 Kelvin is the same as 0 degrees Rankine, but each change in Rankine is similar to the change in Fahrenheit, hence how we got this formula. And now for the second part, find the relationship between TR and TK. Okay, so 0 Kelvin is there. It's equal to 0 Kelvin is equal to 0 Rankine, but Rankine changes like Celsius. I mean like Fahrenheit, and just trying to make sure here I can explain this right. Rankine changes like Fahrenheit, but Kelvin changes like Celsius. So to get that relationship together, we're going to need to replace certain parts. So with that being said, if you want to compare these into Kelvin, we have to first convert these Fahrenheits back into Celsius. So we have now to work step by step change in Rankine is equal to x degrees Fahrenheit minus 459.67 degrees Fahrenheit. And the way we change it to Celsius, we subtract 32, and then everything is multiplied by 5/9. Okay, so this is how we're going to get it versus Celsius. Okay, so we have now it's going to be now 459.67 minus 32 again, so now we have negative 491, and there's going to be times 5 divided by 9. Okay, so then that's y degrees Rankine is equal to, just to make sure we have this here, 5 over, well, x degrees Fahrenheit times 5/9, just to make sure, yep, x degrees Fahrenheit times 5/9 minus 273.15. Okay, so just to make sure, yep, we've done that. And then, well, actually we can just do Celsius, because that's not what we've converted to. We now have the Celsius. Okay, and then if we want to go from Celsius to Kelvin, okay, all we have to do is just add 273.15 Kelvin. So the y change in Rankine is going to be equal to 5/9 x, well, Kelvin. This would be the relationship, well, 5x/9, just to make it a little bit different. That way you can separate those. And that would be the relationship between the Rankine and Kelvin. Okay, so with that being said, let's see how we did. Exactly, we have this, and then when we broke it down, we were able to get from Fahrenheit to Rankine is going to be right here, 459.67. Oh, I think I have my units backwards. Yeah. Oh, I see. Because then so you have to now move it over there to get back to Fahrenheit. So I did the addition backwards, but it should be plus, not minus, because 0 Rankine is negative 459.67. So that means 0 Fahrenheit is 459.67 Rankine. So that's why we have to add it there. So with that being said, this is going to be a plus. So it's going to be plus 273.15. And if you want to go from Celsius to Kelvin, you're going to have to subtract that. Okay. And then that's how we got this. So we still end up with the 5/9 relationship. Okay. And as you can see here, TR divided by 1.8, which is the same thing as multiplying by 5 and dividing by 9. Okay. Because 9/5 is 1.8. So this is what we have here. Or maybe I got it backwards again. Interesting. So it would be Kelvin is equal to 5/9 Rankine. Temperature Rankine. Okay, so where did we go wrong here? Because that one, it does make more sense, and it is indeed correct. So okay, I see now. So exactly, we add there, but if we wanted, it was actually the misstep was right here. Okay, if we wanted to go from it's like we're subtracting the 32, which is correct, but if we wanted to go from, actually we're going to have to add the 32 here. Exactly, so it'll be plus 32. Okay, I think I see where we're going wrong here now. We have to add the 32 and multiply by 9/5. Okay, to go from Celsius to Fahrenheit, which is what we were trying to do here. That is an equation you have to factor in. And then from there, we have to then subtract 273.15 Kelvin, because we're trying to go from Celsius to Kelvin. So I have to take that away, which will make these cancel out. And instead of it being 5/9, we have 9/5. I just have it flipped the other way because the Rankine is now here and the Kelvin is now there. So if we wanted to make sure that things were consistent, because I always have the Rankine there, it is still going to be 5/9. Whoops. Sorry. It's going to be 9/5. 4. Like that. Okay? Because they have the Kelvin and the Rankine, but I have the Rankine and the Kelvin, hence why it almost looks backwards. But these two are the same thing. This is nonetheless correct. And now let's move on to the next question. Question 4. What is a compound name of Cu2O? Okay. So the way we're going to break this down is we're going to separate by their constituents. So Cu, that would actually be copper on the periodic table. As you can see here, on the periodic table, Cu, copper. All right. And O is known as oxygen. So the first thing you have to note is that based on this, we have copper and oxygen together, and that is a metal. Even though it's a transition metal, it's still a metal and a non-metal bonded together. So together we have an ionic compound, which follows its certain naming rules, which effectively goes with ignoring the subscripts. Okay, so now when it comes to at least naming, but you just have to apply the subscripts when it comes to now assigning like what type of charge there is. So oxygen, when you think of the oxidation number for oxygen, it typically likes to be -2. In fact, you can see it on the periodic table that oxygen is on the 16th column, and those prefer typically, specifically oxygen in this case, it prefers to just add 2 more electrons to fill its octet rule. So there's one oxygen, if I wrote it like this, Cu2O, if one oxygen with -2, to still get a neutral element, which is a key here, a neutral element, you now have to have a +2 from the copper. And there's 2 of them, meaning that copper is +1. So this is a copper 1 ion. So like I said, you don't really use the subscript, but for transition metals, the key thing is that they have different types of ions they can produce. Like copper can be copper 1 or copper 2, and there's iron that can be iron 3 and iron 2, and those usually denote how many electrons it's being able to give away. So with that being said, we have copper 1, because in this case each one is +1, oxygen. But we're not done yet, okay? When you're naming really any, well, not any, but most molecular compounds that have a cation and anion, the anion side, the ending has to be fixed, okay? We don't have oxygen. We replace the Y part with oxide, okay? This is how you're supposed to finish off the anion part of naming molecular compounds. So the compound name for Cu2O is copper 1 oxide, okay? So let's see here. Yep, it's ionic. Copper's +1 because oxygen -2, and we get copper 1 oxide. This is correct. And now for question 5. For this question we have, what is a relative mass formula for magnesium nitrate? Okay, so right away, relative mass, think of it as solving for your molecular mass. And technically, yes, this is relative because molecular masses can vary based on the type of isotopes that are actually forming that compound. But in this case, what they're saying in terms of this is that they want you to gather all the different atomic masses of each component of magnesium nitrate and add it together to get a total atomic mass, if that makes sense. But now let's say we weren't given what magnesium nitrate was. We can still use our periodic table to figure out what this molecular formula would be. Magnesium would just translate straight to magnesium, Mg. And because it's on the second column, we know it comes as a 2+ ion. Nitrate, on the other hand, is something you have to memorize, okay? Where it will be nitrogen and a certain amount of oxygens. For nitrate, the ending in ATE, it's NO3-, okay? So when we have a 2+ and a 1-, the only way for the charges to be a net of 0 will be 2 of the nitrates. So our formula, as it shows there, is MgNO3 2. This is indeed our formula for magnesium nitrate. Now, with that being said, to find the relative mass, we have to add up the constituents. So we have 1 magnesium, we have 2 nitrogen, and we have to do like multiply like that. And so that means if we have 2 nitrogen, we have 6 oxygen, okay? And then we get the molecular or their atomic masses for each. Magnesium from the periodic table is 24.305. Nitrogen is 14.007. And oxygen is 15.999. So when you multiply these, we still get 24.305. Okay? And then we get also for this 2 times 14 is 28.014. And then when we do this one, it will be 63 point, whoops, not 63. It will be 95.994. And then we'd add all of these together because you have to add up the constituents. So it'd be plus 28.014 plus 24.305. Okay? And in total, we get 148.313 grams per mole for the relative mass for magnesium nitrate. Okay? And let's see how we did. So exactly, they have the atomic masses of each, which is here. 24.3 is what they use for magnesium. And then for nitrogen, they use 14. And for oxygen, they use 16. And together, they got 148.3 atomic mass units. I prefer to keep it in grams per mole, just because that's usually what they're asking for the molecular mass. But for this question, just to keep it similar, 148.313 atomic mass units also works in this case as well, because either way we know that it's the relative mass because we don't know exactly which isotopes are being used. So that's why we usually generalize with the relative mass, aka the molar mass. And now question number 6. A weighed sample of iron, okay, is added to bromine, okay, and reacts completely, aka there should be no iron left, theoretically. The reaction produces a single product, okay, one product that can be isolated and weighed. And the experiment was repeated a number of times with different masses, but with the same mass of bromine. See graph below. So exactly, we have effectively this. This is our graph that we're working with. Okay, and we can see here that this will be 11 based on the peak, and this right here was 2. And yeah, that is really all the information we kind of need right now. We have mass of iron and then the mass of the product. So with this being said, let's start with question A. What mass of Br2 is used when reaction consumes 2.0 grams of Fe? So for this is going to take multiple steps, because the first thing we have to do is find out the in a sense the formula that we're even working with here, because as we know with iron, because it's a transition metal, it can have different types of like iron 2 versus iron 3, but we can see here, right, the mass of iron is going to be 2 grams of the 11. That means bromine had 9 grams of bromine had to be used. No, sorry, actually no, it still makes sense. 9 grams of bromine has to be in that mass of product if it reacts completely, because it used up all the mass of iron. So that means the only mass left has to be bromine, which is 9 grams of bromine. Okay, and now what is a mole ratio of bromine to iron in this reaction? So we say 9 grams of Br2. Okay, and that's important to note, because the fact that when we're doing the mole ratio, we're going to have to use Br2 as the molar mass and not just bromine by itself. So mole ratio of Fe to Br2 in reaction. So we have a grams ratio of 2 per 9, because it looks like 2 mass of iron was used per 9 mass of bromine of Br2 to produce the mass of the product. So with that being said, we have now, just as a double check in terms of the moles, we would need to convert the iron first from the mass to the moles. So iron by itself has a molar mass, a molar mass of 55.845 grams per mole. And if we start out with 2 grams, okay, to get rid of the grams, we need to divide. So that's 1 mole is equal to 55.845 grams. And so we realized that what we're dealing with for the grams was actually just 0.0358 moles of iron. Now bromine, as we said, we have 79.904, but because we want to do the molar mass of bromine gas or liquid, it's still Br2, so we have to multiply that atomic mass units by 2. So we have 9 grams, okay, divided by 1 mole of Br2 is 159, because 79.904 times 2, 159.808 grams. So 9 divided by that, we have 0.0563 moles of Br2. So if we're to just divide these together, okay, as in to get the ratio, we will divide the iron by the lowest number, so that's 0.0358 to get ratio of 1 so far, and it's going to be 1, 2, as in 0.0358. This ratio here is going to be 1 to about 1.57. So a little bit unclean, but if we were to, I guess, kind of do an estimate, we would have almost, okay, a 1 to 1/2 or a 2 to 3 ratio. That's what we have there. Okay. So what is the empirical formula for this product? So if we have for every 2 iron, there's 3 Br2, okay? That is 6 Br. So that way we have FeBr3. That is what we have here. But realistically speaking, because we had established a 2 to 3 ratio, the empirical formula has to reflect that. So we actually have Fe2Br6. This is what I would put for now, which is the empirical formula, because when we solved for the bromine, we would see that it had Br2. And if we got a 2 to 3 ratio, we have we have 6 Brs in total. So we put C, empirical formula, okay, and then it's asking for the balanced chemical equation. Okay, for this, and because we have Fe2Br6, we can actually do, and I guess simplified form, we have Fe2Fe solid plus, and let me check here, what's it, liquid bromine, perfect. So liquid bromine, so that would be 3Br2 is going to turn into, now we can kind of put it this way, where it's 2FeBr3. So I'm kind of competing this one. I think it would be best just to put Fe, because it has it there. Yeah, I'll put Br6 here for now. That's what I'm thinking, but this would be the equation we're working with here. That is what we would have for the product. Now the name of this, okay, we have iron. Okay, so right now it's asking for the name of product. So we have the iron, okay, and we have the bromine. So iron, bromine, but bromine, the oxidation number for bromine, because it's a halogen, it'll just be -1. And if there's FeBr3, if we have a -1, there's 2, then that's -3 in total. So iron needs to be +3 to make up for it. So now we know iron's charge is going to be +3. So based on that, the name of the product is going to be iron 3 bromine, but then you drop the INE and replace it with IDE, iron 3 bromide. That is the name of the product. And then F, which statement or statements best describe the experiment summarized by the graph? When 1 gram of iron is added to Br2, iron is a limiting reagent. Okay, we'll keep a note for that. When 3.50 grams of iron is added, there's an excess of Br2. You notice that even as the mass is increasing here, there's no more product, because now we've run out of bromine here. When it hits a plateau, like right here, it's because we've run out of product. Oh, sorry. There we go. We've run out of product. I mean, not product. We've run out of bromine gas. Here, in this whole increasing, not the plateau yet, iron is the limiting reagent. Okay? So, with that being said, if asking for best statement, so far 1 is correct. 2, we see that there's no more of the bromine gas, so that's incorrect. 2.50, both reactions are used up completely. So as you can see here, it's actually 2, this point right here, where both are used up completely. So 0.3 is also incorrect. And then number 4, when 2 grams of Fe is added to Br2, 10.8 grams of the product is formed. The percent yield must therefore be 20%. So let's see here. It looked like 11 to me. Maybe it is just 10.8, which would make a lot more sense if my math looked a little bit off. But nonetheless, though, we have 10.8 grams of product is formed. The percent yield must therefore be 20%. This would be, because 11 grams is formed, percent yield is based on the how much was actually formed versus the theoretical value. So 2 grams of iron, as we saw here, was this much moles. And using this formula here, okay, we see that it's a 1-to-1 ratio. So we would actually get the same 0.0358 moles of this. And then converting that over to a, I guess the molar mass, we have going to be, so iron 3 bromide, based on the periodic table, is going to be 55.845 plus 3 of bromine, so that's 79.904 times 3. Alright, so that's a big molar mass of 295.557. Okay, and now we multiply that by that number, the 0.03, to see how much we would actually get. Theoretically, we get 10.58. So somehow they got more product formed than even possible. So the percent yield would actually be not 20%, but just because it would be 10.58 is a theoretical. So 10.8 minus, well, actually just divided, 10.8, and we have to find the I guess, divided by the 10.58, our percent yield is 102%, okay, which is not correct either for number 4. So the only one that's the best statement here would still just be the first one. And with that, let's see how we did for this, okay. Yes, so 2 grams of the 11 gram product make 9 grams of Br2. So now we have 9 grams divided by 159.808, and we get 0.56. They rounded to 0.6 there and 0.4 here, but we still get 3 moles of Br2 and 2 moles of Fe. So the empirical formula, I still have Fe2Br6 just because I wanted to just translate directly, but that is correct, FeBr3. And we still get the same balance equation, which is perfect. And the name is indeed iron 3 bromide, and only one is correct, okay? 11 grams of the product is formed when 2 grams of Fe is added. The percent yield is 100% and not 20%. So the reason why this one's a little bit sketchy, just because exactly as we calculated our theoretical percent yield based on the amount of iron there was, should have been like 10.5 something. But let's say based on the fact that it was 11 on the graph, we would actually still have 10.8 divided by 11 times 100 to get a percent yield, and that's 98.18. So it's nowhere near 20% yield. So this is still correct. And we can move on now to question number 7. Okay. How many orbitals in an atom? So orbitals in an atom can have this designation. Okay. So with this is a combination actually of using your, in terms of the theoretical numbers, what are they called? The where we have the N, L, ML, and MS. Those would be like your orbital notation number, like your VSEPR theory. Just blank it out on the actual name of it. Nonetheless, the ones we're focusing on here for this question is these two, okay? The L and ML, okay? Because 5p, all right? That one, to be able to say the orbital, so we know it's L because it's a p. So then with ML, okay, p simply can only have 3 orbitals in it. It'll be the whole, because p for L, when it's p, is equal to 1. So we have ML of -1, 0, and 1, which connotes to 3 orbitals in there. So with that being said, this question, it would only have 3 for 5p. For 3dz2, z in the L, okay, stands for 2, and ML is -2, -1, 0, +1, +2. But 3dz2, because we have this z2 part, is emphasizing just one of those 5s. Fortunately, it is one of the things you have to memorize. We actually have it here. Okay, so if we went over to our orbitals, you can see here that the 3dz2 is just a specific type of orbital here, and this right here can only fit 2 electrons because it's only 1 orbital. So this is what it's referring to here, and that would be just 1 for the 3dz2, because only specifically referring to one of the 3Ds. Now 4D, okay, same thing here where we apply the ML of the 5. You can see here 1, 2, 3, 4, and then the 5th one. And because it's not saying like Z2 or anything like that, this one would have 5 orbitals that can have that designation. Now, if n was equal to 5, so now this is starting at, theoretically, because our n is 5, our L is going to be 0, 1, 2, 3, 4, making our ML, okay, is going to be now 0, -1. Well, just to make it easier for ourselves, 0 would only translate to just 1 orbital because it's just 0, and this, as we showed up there, is 3, this is 5, this would be 7, and this would actually be 9. So if we added all of these together, that would tell us how many orbitals we deal with if n was 5. So that's 9 plus 7 plus 5 plus 3 plus 1. We have 25 possible orbitals with that designation. And if n was 4, okay, we fall kind of like this, where L would be 0, 1, 2, 3. And in a sense, we're just canceling that 9. So we would have 25 minus 9, 16. Okay, this is the possible orbitals. Okay, 2 times. Okay, and just to make sure, for the possible orbitals, the way you can actually calculate it as well, just to see if my math is correct here, we have 1, 3, 5, 7. Yes, so exactly. So this is what we'd have here. We would have 1, 3, 1, 5, 25, and 16 possible orbitals. So 3, 1, 5, perfect. And then 25, 1, 3, 5, 7, 9. And this would be 16. And this is correct. And now let's move on to question number 8. We have, what is a Rutherford model of the atom? So this is more of a conceptual question, and this is based on what even Rutherford was testing. So what he did to find his model, right? Imagine this. He had a gold, he had like a gold plated sheet, all right? And what he'd do is use like a tiny little laser, and I am just ad-libbing a bit here, but he uses a tiny little laser, and he would, in a sense, shine it through and try to note, and he would choose to select different points, but in a sense he would try to note how much it refracted, or like how much like it was changing direction. So the gold sheet was very thin, and the goal, in the sense, what he was trying to do was to see if he could pinpoint if there was spots to where there was a great change in like because like the gold, he kept shining lights in different spots, and he noticed that they would change directions, and the goal was to see where there was great change based on where he would shine it. And based on that, okay, he found that there were certain spots to where that beam would be refracted by quite a bit, but then kind of around it you could almost shine through it, almost in a sense, or you would reflect off very tiny little things. So that's how he was able to develop the theory that we have a nice center nucleus with then smaller things orbiting around it. And then, next to that would be like another gold atom with the same thing. So based on like the fact that he would shine the light, it would depending on how he move it, he could have shined it like right here, and it could have gone straight through, or he could shine it here and reflected off, or shine it here and reflected off. Just things like that, to where it's like, okay, now I'm starting to visualize that there is a concentrated spot in certain areas to where my beam is being heavily reflected off of it. Okay, so that's how he came up with the idea. And the important thing here to note for the Rutherford model is that, yes, exactly, there is a larger concentrated nucleus surrounded by smaller tiny particles floating about of it. And that is how we have the Rutherford models. Okay. So he was the gold foil experiment, exactly. He was shooting some particles through, and then he realized like there was a dense core in there. So that is how he found that, and this would be an example of the Rutherford model of the atom. But the key thing here to understand is how he got his model, which is through that gold foil experiment. Because there are some models that look quite similar, like the Bohr model and all that stuff, which do look very similar, but have each of their differences based on how they came about it. So this is correct nonetheless. Let's move on to question number 9. We have, what is matter? Okay. Substance being dissolved in solution. B, anything that occupies space and has density. C, basic or fundamental substance that can't be broken down further by chemical reaction. And then D, we have smallest unit of an element that has characteristics of the element. So with this being said, if we go through this, matter, so substance being dissolved in solution, that would actually be solutes. A solute is what's being dissolved, and the solvent is what it's dissolved in. So this is not going to be correct. It's not going to be A. B, anything that occupies space and has density. That is pretty close to a definition of matter as I've seen one, because that is the goal here. Basic or fundamental substance that can't be broken down further by ordinary chemical reaction. This sounds like a molecule of anything instead of a not too sure about this, but it sounds like a molecule. And the smallest unit of an electron, of an element that has the characteristics of the element, would just be an atom or an electron. Maybe this is an atom and this would be an electron, possibly. We'll see. But the point being, though, is that it's not matter. The one that's matter would be anything that occupies space and has density. That's the key for matter, okay? Matter cannot be, I guess if I remember correctly, created or destroyed. Matter is constant throughout the universe, unless we deal with the whole like Big Bang theory where, you know, we have a spot where matter is constantly being expanding and such. But point being is that when we're dealing with a lot of the calculations and stuff, matter cannot be created or destroyed, it only changed to different forms. And so things like this pen, me, my tablet, we take a space, we have density. This is all the things involved in matter. Okay? So, as I said, A is a definition of solids. The definition of an element is going to be C, and D is the definition of an atom. So close, but point being is that the best definition of matter would be B, and this is correct. And now let's deal with question number 10. We have, for question 10, how many cups in 1 pint? So hopefully this can be answered in our conversion sheet for liquids, but the point being is that we actually start with pints and we want to go to cups. So we have X amount of pints. In this case it would be 1, but the goal here, to get the pints units to cancel out, we need the pints to be in the denominator and cups to be in the numerator, and then we'll be able to get our formula here. So units of volume, okay? Once again, something that we do not have, a pint. It's not a common thing to measure things out of, but still nonetheless, pints to liters. Let's start there actually. That way we have multiple steps. So with this being said, well actually we don't know what liters to cups is either. Well actually we can do that after, but that's okay. So X pints is equal to, so that's 1 pint is 0.473176 liters. And then we do the same thing. We want to get rid of liters, okay? So we don't know yet. We want liters to, maybe we can have it here finally. Do we have any cups? No, we do not have any cups, unfortunately. Liters to cups, though. We have 1 liter is 4.22675 cups. So if we cancel out the units, liters are gone, pints are gone, and all we're left with is cups. So effectively, we have 0.473176 times 4.22675, and we get as close to 2 as possible. So I'm just going to actually round it. It's going to be 2 cups. And in this case, because we were dealing with X amount of pints, it would be, for every X, there's 2X of cups. This is going to be it. So if there was 1 pint, if we did 2X of it, so 2 times 1, it'd be 2 cups. If there's a 3.5 pints, it would be 7 cups. And that is exactly what they got here. So this is correct. The important thing here is just showing how you cancel your units. That would be how you solve these questions. And now, let's move on to question number 11. But before we do that, just a quick little water break. Okay. Well, I can still read it out. We have, right, what is a balanced equation for the reaction between acetic acid and sodium hydroxide? So, acetic acid and sodium hydroxide. And we want the balanced chemical equation. So first thing, we want to be able to identify that sodium hydroxide, okay, is a strong base because it has hydroxide in it. So that's NaOH. So with that, the separate formula for it is going to be Na plus OH minus. Whoops. NaOH turns into Na plus OH minus, okay? So now acetic acid, right, is going to be CH3 COOH. And I know that acetic acid is not a strong acid, but to be able to find out for sure, we actually have the acids and bases list here. And acetic acid is all the way down here, a weak acid. So we usually denote by this formula of CH3COH plus water. Okay. The key thing here is this arrow, because there's not a complete association. It can go back and forth till we have CH3COO minus plus H3O plus. Okay. And now for the last part, if these two are going to dissociate like that, then we see that the products formed are OH minus and H3O plus. And as you can see here, hydronium ions, they work pretty good in terms of, I guess, being a strong acid. But the goal here is that when we have this, we lead to 2H2O. So then together, what we're left with is Na plus OH minus plus CH3CO, COOH. That would go into CH3COO minus, and the Na plus would form this, and then we have plus, because it has, oh, I almost forgot, plus H2O is the last part, because we still need that water, and there'll be 2H2O. But because we have H2O and 2H2O on each side, we can actually cancel out one H2O, because that was the one from here, and this right here would be our completed formula for acetic acid reacting with sodium hydroxide. H2O, the CH3COH plus NaOH, CH3COO plus H2O. And exactly, this is going to be the balanced chemical equation, because as you can see, 1 to 1, OH, H3O, and then we're able to cancel out one of the waters. So this would be our formula, and this is correct. And the only reason why I have the Na and the OH separate is just because for strong bases, when they are put in water, they do just dissociate completely. And if we were assuming that this was put in like an aqueous solution, this is what we would actually be working with. So that's how the Na can now be attacked by the CH3COO minus, and the H proton, that was just taken away by the OH minus. Okay. And now for question number 12. Write the balanced molecular equation for the neutralization reaction between H2SO4 and KOH in aqueous solution. So the tricky part here is that we need to first understand how H2SO4 would even have to neutralize. So we have H2SO4 plus H2O, okay, and it is a strong acid actually, the first one, or is it? I was confused. Sulfuric acid is actually, yes, it is a strong acid, the first one. So it dissociates completely to where it gets HSO4 minus plus H3O plus. And then that HSO4, okay, plus H2O turns into SO42 minus plus H3O plus. Okay, that is the steps it will take for SO4 to get rid of all the protons. Now KOH just turns into, and this would just be like that because it's a weaker acid, but KOH is associated to K plus and OH minus. So in order for this to actually balance out, okay, we have 2 H3O. This OH minus has to happen twice. And that would be the only way, because in this case, we need the 2 OH minus to neutralize the 2 H3Os. So we would actually have, and if we wrote this whole formula, these two would cancel out first, and then everything else will stay. So we have H2SO4, okay, plus 2H2O plus, right here, 2, well actually we can just write this part because they are dissociated in the water, but here 2K plus 2OH minus turns into, and then we have these two here form the K2SO4, okay, and then now we have 2 OHs plus 2OH minus plus 2H3O plus, and actually together these two are actually just 2H2O. So with that being said, now we have 2H2O here and here. So really what we have in total, just to make sure, K2SO4, spectator ions, thing, just to make sure, 2H3O plus 2K plus 2OH minus K2SO4 plus H. Okay, just to make sure I have it correctly done. We have 2H3O, 2OH. Oh, I see where. So instead of this, we would actually have, so we have the 2H3O, yes, but the OH minus is still going to be there as well. And as well with the, so this is where the H pluses are, H3O. Oh, okay, I definitely miscounted. There we go. So we have 2H3O plus O minus. So to get to H2O, 2K, 2OH. So that would be in total. I want to make sure I write this right, because if I take 2, oh, okay, I see what's happening. 2 hydrogens can go over there. So then in total we have 4H2O. That is what I was missing there, because these two don't just form 2H2O. We have 6 hydrogens and 2 oxygens here, and 2 hydrogens and 2 oxygens here. So to balance out to 4 and 2, you have to move 2 hydrogens over there. So that's why we have 4H2O liquid. And now we can actually see here, the 2 cancels there, and then the 4 becomes 2. So what's left over in the equation is H2SO4 plus 2 potassium. And don't forget your aqueous sign. Okay, plus 2OH minus aqueous turns into, and what we have left is K2SO4 aqueous plus 2H2O liquid. And as you can see, this will be balanced because we have 2K replacing the 2H, and so that's why we can get the 2H2O, because we have 2OH minus, just need a proton. And let's see how we did. So this is the first, just writing everything out, and this would be not balanced quite yet. So now after they balanced it, they have 2K and 2OH, and then they got the K2SO4 plus 2H2O liquid. Perfect. So this is going to be the balanced equation, and this is correct. And the only reason why I wrote the K and the OH separately, just because for strong bases, they dissociate completely. So that would be theoretically what would be in the solution. We have potassium ions and hydroxide ions. And then technically would have HSO4 ions and H3O, but that would be a little bit complicated. So question number 13. For this one, we have, what is a mass of solute in grams in 250 mils of a 0.0125 mole solution of KMnO4? So we have 0.0125 moles solution, and we have 250 mils of it, and they want to know what is the mass of KMnO4, and this would be potassium permanganate, something like that, or just potassium manganate. Let's see the acids. MnO4, no, that wouldn't be an acid, or maybe it would. Let's see, H, or would it be MnO4? I'm pretty sure that would be permanganate. MnO4, perfect. So that is potassium permanganate. So back to the question. We first need to find out how many moles we're working with. So as you remember, okay, we have the moles per liter here. To get rid of the liters, just have moles, we need to multiply by the volume. So we have 0.0125 moles, so it'll be moles per liter of potassium permanganate. And then we're going to multiply 250 mils. But as you notice, these units don't cancel out. So we actually need to divide by 1,000 mils per liter, because 1 liter is 1,000 milliliters. So you see here, these two actually end up canceling out, because now numerator denominator, and these two also cancel out. So by multiplying by 250 and dividing by 1,000, we get that the amount of moles we have, 0.0125 times 250 divided by 1,000. We get that we actually have 0.003125 moles of potassium permanganate. Now to find out how much of that is grams, we need to now know our molar mass. So we first need to get the constituents. So we have 1 potassium, 1 manganese, and 4 oxygen, okay? And so with that being said, look at the periodic table. We have potassium is 39.098, manganese is 54.938, and oxygen is 15.999. So when we add these together, we have 39.098 plus 54.938. Let me just make sure. Plus 15.999 times 4, which is 63.996. Okay. And then we add them together, and we get our molar mass is plus 54.938 plus 30, potassium is 39.098. We get our molar mass to be 158.032 grams per mole. So we're given this really small moles. So now to find out how much of that is actually grams, we need to multiply it by the grams per mole. So 0.003, okay, moles times 158.032 grams per mole. So then the mole units cancel out, and then what we get is 0.003125. We get 0.4938, and 385, and we want to see how much we should round it. And because we were given 250 mils, that's 2 significant digits that we're going to work with, because that's the lowest one. The other one is 3 significant digits. So if we were to round it properly, we just get 0.49 grams of potassium permanganate. So then that's what we did here. And then so they got the mass, which it would be the molarity multiplied by 0.250 liters, which is effectively what we did here, 250 divided by 1,000, and then multiply that by its molar mass, and we got 0.49 grams. And this is correct. And now let's move on to question number 14. And this question here is asking, what is the rate law for the following mechanism? Okay, so we have step 1, okay, rate law for following mechanism. So this is more of a conceptual question. I'll show you why. Okay, step 1 is A plus B C. Step 2 is A plus C D, and overall 2A plus B D. And as you can see, it makes sense because each part cancels out. Theoretically, we have the C's here that cancel, and so we have 2A plus B turns to D. So this makes sense. Now, the one point that they mentioned was that this is slow and this is fast. So our rate law typically is going to be rate is equal to K reactants, okay, to the power of whichever value. That is just a structure for the rate. Now, when they're kind enough to break it down to its actual step-by-step of how the reaction occurs, the rate law of the whole reaction is determined primarily by the slow reaction, because that is, in a sense, the limiting reaction. That's a reaction that's going to take the most time to complete. So if this is fast, this happens not almost, but this happens like instantaneous. So this is the one that determines how fast it's going to go. So the overall reaction is going to be the reaction it takes, the rate reaction for step 1. Okay, and we see here what reactants we have here. So the rate for the overall reaction is just going to be K, whatever the rate of this is, and then it's going to be these 2 products. Now, with this being said, is that if we use the overall reaction, we've gotten that the rate, because when we have this, okay, the way it works is that this becomes our coefficient. So we would have gotten rate is equal to K overall, so KO, A squared B. All right, that would have been something that would have thrown us off because of the fact that, oh, we just see the overall reaction. But because we have to use the concept that the slow reaction determines how fast the reaction would go, this is actually what we end up with, because it would actually be based on this. In fact, if we were to even write this overall reaction, we would actually see, like experimentally, that this rate here for the overall reaction would be very close, if not almost the same, as this rate here for the first step. If for some reason they said the step 2 was the slow rate, our rate overall would be K2 for the second one, A, because we still have a coefficient each time of 1, C, that would be our rate if it was slow for the second step. Okay? As you can see here, the reaction mechanism and the rate law is obtained by comparing reaction rates with reactant concentrations. Okay? And the rate determining step is the one that goes slower, the slowest step in the actual reaction. Okay? So with this being said, exactly, our first step is a rate determining step because it's a slower one. So then the first one has a K1 and then the other one has K2 as I showed here. And because then we're trying to find out the overall reaction and we have that rate determined step, that is going to be the one that determines your overall rate period. You would see though experimentally that there would be slight variation between, like if there's a way to isolate the first step versus doing the whole reaction, you'll see that there's a little bit of variation, but you will see that those two will be very similar to each other because of the fact that the rate determining step is going to be the one that determines the overall rate, because step 2, as you see here, is the fast one. It happens instantaneously, so it'll be very hard to compute that rate there and how much it factored in. Nonetheless, this is correct. And let's move on now to question number 15. Okay, which has a greater O-NO bond angle, NO2 or NO2 plus 4, NO2 minus or NO2 plus 4 bond angle? So with that being said, we need to first figure out what the Lewis structure for these would be. So nitrogen, okay, how many electrons it offers? It is on the 15th column, okay, and for those ones, they have 5 electrons they can contribute. And you can actually also see this by doing the electron configuration. You'll see that it ends in 2p3 plus the 2s2. It will be in total 5. Oxygen, you see it's in the 16th column. So with that being said, it can offer 6. And same thing here, 5 and 6. But there's 2 oxygens in each one, so that would actually be 12. But we have this minus here, okay, meaning we have an extra electron. So 5 plus 12 plus 1, that'd be 18 in total. And for this one, it would be 5 plus 12, but there's a positive, meaning that'd be minus 1. So 5 plus 12 minus 1, we have 16 electrons we are dealing with, okay? So let's first draw out the Lewis structure for NO2 for the 18. So we have nitrogen in the center, and we have 2 oxygens, okay? And oxygen are here. Oxygen now, it needs to incorporate the rest of its 6, so it'll be 2, 3, 4, 5, 6. Same with this, 2, 3, 4, 5, 6. And nitrogen is right now sharing 2 of its 5, so 3, 4, 5. So what can actually happen here, okay, is that these 2 will be able to go over here to form a double bond. In fact, let me just draw it a little bit better. Make this nitrogen alone up here. Oops. 4, 5. and these two will form here into a double bond. All right, and then we notice that we have this lone pair here, right? Well, thankfully, as was stated earlier, we had one extra electron, so that's where it would go there. So NO2 minus, that anion, would be like this, where it has one, but over here, as we mentioned, it'll be a double bond, and it'll be there. Still a lone pair on the nitrogen, and this. So this would be NO2 minus. And the theoretical formal charge for each, it would be nitrogen, it likes to have 5 electrons based on the periodic table. So it would be sharing, well, not sharing 2 electrons, and sharing 6 electrons. So that's 2 plus 3, that's 5, so it's 0. The oxygen to the left is 6 minus, it's not sharing 4, but it is sharing 4. That's 4 plus 2 is 0, perfect. And the oxygen on the right, 6, it's not sharing 6, but it is sharing 2, and that's 6 plus 7, so that's minus 1. And it makes sense because that's where the negative charge is for NO2 minus. So that's what we have here. To determine the electron geometry for this, okay, it would be, it's attached to 3 things. So 1, 2, 3. So that means 3 electron geometry, and that is a trigonal planar for it. And then because it has 2 bonds and 1 lone pair, the shape is going to be bent. And so we just kind of know it looks like this. The lone pair right there. And the angle is like around, if each one was 120 degrees, it would be less than 120 degrees. That's what we know. All right. So there's a 2:1 ratio bent. Now for NO2 plus, this one is going to be drawn very similarly as what we just did. Okay, where we have the oxygens, and then we have oxygen wants to have 5, 6, 3, 3, 4. Yep, that's done there. And now nitrogen has 1, 2, 3. Now I'm actually going to take out 1 electron, and I'm going to choose this one here because if you notice, now we actually have 16 if you counted it. So it's 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you can see here that these ones would form that double bond along with these ones to form a double bond. So NO plus, just by getting rid of 1 electron, would be like that, with these bonds here and these bonds here. So with that being said, the formal charge would be 5 in the middle. It's sharing now, as you can see, has 0 by itself, but sharing 8. That would be plus 1. So the nitrogen is where that plus 1 is going to be, which makes sense. And you should see actually the oxygens are each going to be 0 for their formal charges, because it will be 6 minus has 4 by itself plus 4 over 2. That's 0. So that's for each side. So there we have it. So for this, as you can see the shape here, it only has 2 bonds attached to it. So it has a formal, electron configuration, not configuration, the electron geometry, it would just be linear because there's only 2 bonds. And because there's no lone pairs, it's still going to be 2, 0. So it's going to stay its linear shape. And with that being said, it's going to look like this, where the bond angle between is going to be actually equal to like 180 because it's a straight line. Okay, double bond there, double bond there. And so they asked in the original question, which has the greatest bond angle? Based on this and everything we've done so far, we have one that's less than 120 and one that's 180. So the NO2 plus, okay, that would be our answer, is going to have the greater bond angle between the two, because based on the Lewis structure and the electron and molecular geometry, that one is going to be a linear shape, while the NO2 minus is going to be a trigonal planar, which goes down to bent shape. Okay, it's like the molecular structure is bent, angle is 115, and this is linear, angle is 180. So the difference is due to the lone pair present in NO2 minus, but not in NO2 plus. And this is correct. Now let's move on to question number 16. How do you complete this reaction of HNO3 plus H2O plus H2O? So HNO3 is nitric acid, which is considered a strong acid, if I remember correctly. Nitric acid, yep, it is a strong acid. So it's going to actually dissociate completely. So HNO3 is going to look like this. HNO3 plus H2O, actually, it's going to be NO3. It's going to be NO3 minus plus H3O plus. This is going to be what we get for these two reacting, and it's going to be a straight line there because the fact that this reaction is not typically reversible unless in some very serious conditions, but the H from the NO3 wants to dissociate completely, and that H is going to be attached by that hydronium. So coincidentally, because when we show dissociation of acids we use water, we actually end up just having the full equation. So this is actually what the equation will look like, and as they said here, that is it. So just to briefly explain this, with strong acids, the key part that I like to emphasize is the arrow. The arrow implies that the reaction doesn't really have any reason to want to go backwards, because the nitric acid is a strong acid, so it dissociates completely to the nitrate ion and the protons, but those protons are actually not protons, but they're things that they're protons that water do take, and in total it forms this hydronium here that we have, which is exactly what this equation has as well. So now let's move on now to question number 17. Okay, what is a formula mass, which is the molecular mass, for ethyl alcohol? So they were nice enough to give us the formula C2H5OH, but if they were not that nice, the way we'd still found the formula from the name is that we use this part right here. Because we know ethane, okay, with the ANE follows the rule of CnH2n plus 2, and eth, okay, means 2 for the prefixes, so we have C2H and then 2n plus 2, that would be 2 times 2, which would be 4 plus 2, H6. But now for alcohol, one of the hydrogens is dropped and replaced with a hydroxide group. So we have C2H5, because that's one of them dropped, and the hydroxide group is OH. And that's how we get that for ethyl alcohol. Now with that being said, we have 2 carbons, 6 hydrogens, because you can see here H5 and the OH, well the H there, and 1 oxygen. And the reason why we don't write this formula as C2H6O is just because it's hard to see that it's actually an alcohol, which is why they write it like that. And there are other isomers with this type of name, but it will look very different from ethyl alcohol. So with that being said, carbon is 12.011, hydrogen is 1.008, and oxygen is 15.999. So that's 2 times that is 24.022. 6 is 6.0. 6 times 8 is 48. And then this is 15.999 still. And so we have 24.022 plus 6.048 plus 15.999 and we get 46.069 grams per mole. And that would be the molar / formula mass for ethyl alcohol. Just remember here that we're adding up the constituents together, and we have to make sure we're including how many of each we have. So let's see how we did. And that is indeed the correct number. The only reason why it's different just because based on periodic tables, which elements and how much their atomic mass would be. For my periodic table, as you can see here, hydrogen is indeed 1.008 and carbon is 12.011 and oxygen is 15.999. Here, they had a periodic table where their carbon was just slightly different along with their hydrogen and oxygen. But the goal is that our numbers in the end are quite similar to each other. So now let's move on now to question number 18. What are the main properties of ionic compounds? So let's actually refer here to what they have. Okay, the properties of the ionic compounds, it's going to be, first thing I have to mention that I don't see is that it's between a metal and a non-metal on the periodic table. Or has typically at least an electronegativity difference between the metal and non-metal is typically greater than 1.6 difference in electronegativity. Because sometimes we're dealing with trickier things here where it's like silicon bonded with oxygen, and silicon is technically like a metalloid, and that one skates the line of whether it's an ionic bond or not. But because the electronegativity difference 3.44 minus 1.9 from the silicon, 1.54, this would be a very tricky thing to say whether it's an ionic compound or not. But this is kind of how we base it. For this, because silicon is a metalloid, I personally would say that this is still an ionic compound, but I may be wrong, because typically you can tell which ones, like when they have non-metals bonded, those are definitely not ionic compounds. Like CO2, carbon dioxide, that is a molecular compound. Nonetheless, in terms of how they bond, as they said here, they form crystal lattices. So it's kind of like instead of it being kind of like a molecule or whatever is bonded type of thing, like when we have carbon, like this would be C4H10, like butane, for example. Okay, this would be like its molecular structure. Usually ionic compounds like NaCl, okay, would kind of form like Cl, and then this would be like Na, and it would kind of keep going like that. It's like it's a weird way to put it, but exactly, it's kind of like that. It's just the crystal lattice structure where you keep switching between Na and Cl, and it keeps going on. It's like a sheet of sodium chloride continuing on and on and on. And that is what they mean by the crystal lattices. They have high boiling and melting points, since ionic bonds are actually the strongest type of intramolecular forces. It goes from nonpolar covalent to polar covalent to hydrogen bonds and then ionic bonding. To break an ionic bond, it takes quite a bit of energy, because of the fact that at that point, those two, the metal and non-metals that are bonded together, the metal has effectively given that non-metal the electron. It said, here, have it. I'm actually comfortable. I don't want it. And that non-metal is actually happy to receive it. So to then send some energy in to pretty much say, nope, both of you have to keep your electrons of what you originally started with, it takes a lot of energy to do that. So yes, that is why it has the highest temperature required to break it. Ionic compounds have higher enthalpies of fusion and vaporization. Same reason, because ionic bonds are just the hardest to break. and they take the most energy to, I mean, not the most energy, but when they are formed, that is the strongest type of bond there is. It has the most energy in it. Ionic compounds are hard and brittle. Think of it exactly like salt again, forming that crystal lattice. That's the reason why it's brittle, just because that crystal lattice structure allows it. If you really zoom in on salt, you'll see kind of like it goes like, it's like striated. And then it's like that, and this would be like like a gram of salt. If you look really close, it would kind of look like that. I wish I could show you actual pictures of it, but that's what makes it first hard and brittleness. Ionic compounds are good conductors of electricity. This ties into the whole how the electrons are distributed, because it's a thing where it's complete donation of electrons to the other one. There are a lot of positive and negative charges on it, which allows electricity to be able to conduct and flow through it. Like the electrons, because the electrons are kind of just everywhere, really, there's a base. I'm putting on the Cl because that's actually where the electrons would be, and there's a way for electrons to be able to travel through this whole crystal lattice structure. And exactly, and this can be actually shown when dissolved in water. We have the Cl ions, and we have and then we have the Na plus ions as well when it's dissolved in water, which allows the electrons to be able to flow through and everything. And more of our ionic compounds are also good insulators. That one, not really sure. Well, I mean, the rest of the list is correct, so I'll have to assume this is correct as well. But the point being, though, the one you have to really focus on is the crystal lattice structure. It is between a metal and a non-metal, okay? And the last thing is that it's the strongest bonds, which is ionic, meaning, as it says there, high melting and boiling points. So that's what we have for ionic compounds. So this is correct. Now move on to question number 19. Name the following alkene. Okay. Name the following alkene. The reason why they say alkene and not alkane is because if you look at the picture right away, you'll see there's a double bond there. And when you have double bonds, it's no longer an alkane where it's fully not condensed, fully saturated, but now there's a little bit of unsaturation there, which is a double bond. Okay, so we have, based on this picture, we have this. I can definitely draw it a little bit better than that. There we go. There we go. And then the bromine part. And then the double bond. Okay, so with that being said, when there's a double bond, actually before we move on there, I'm actually going to use color coding to go through this. We have the longest chain here. We go like this: 1, 2, 3. This chain, 6. Okay. So there's double bond here, but point being is that we have 6 chain as our longest chain. Okay, we have 1, 2, 3, 4, 5, 6, 7. Actually, whoops, definitely miscounted. Let me just 1, 2, 3, 4, 5, 6, 7. Okay, perfect. So 7. Okay, so because we have 7 as our longest chain, we know that the ending would have to end in hept, because hept means 7. Okay, so at least we have that part named. All right, so now the trick here is that when we're actually numbering them, so not this, we have to number to put the, I guess, most important part, and each part is ranked differently. But the thing is that we want to be as close as we can to the double bond, because that's actually what defined this. It's an alkene now, So we actually, the way we number it is we start from the right side because that's closer to where the double bond is. So we have 1, 2, 3, 4, 5, 6, 7. Okay? And so we can actually say that this is hept 3 ene, because this is saying that is where the double bond is located. We don't say that at the 4, we say it starts at the 3. Okay? And now, what other parts do we have? We have this part that sticks out, and we have the bromine as well. Okay? For these, at 3, we have 3, and because it's just a 1, that's just CH3, that's 3 methyl. And this, on the 5, we have 5 bromo. That would be how you would name there, because the way it works is that you have bromine, we drop the INE at the end and just add an O. Typically, that's even if you had a chlorine, for example, it would be chloro, and a fluorine would be like fluoro. But for here, we have 5 bromo. Now, here's the trickiest part, in my opinion, about how to order them. My first instinct would be to put 3 methyl 5 bromo, but that would actually be incorrect. What you want to do is organize by the letter alphabetically. So we actually have, for this name, 5 bromo. I can definitely write that better. 3, I wish I had more space. There we go, more space. So 5 bromo, 3 methyl, hept. Let me just keep it like that. 5 bromo, comma, 3 methyl hept 3 ene. Because on the 3, there's a methyl group. On the 5, there's a bromo group. But on the 3, there's both methyl group and where the double bond is. And this right here should be the name of the following alkene mentioned. Okay, let's see how we did. 5 bromo, 3 methyl heptene. So they do have comma here. Depending on how they want it to be done, I like that better of using the dash rather than the comma, because usually the comma is used to separate, like if there was I guess in the situation where they had 2, it'd be 5. No, that's not a good example. If they had a bromine also here, like Br for example, it'd be 5, 6 dibromo. So that's where the comma will be used. So I would keep that noted for future. So 5 bromo, 3 methyl heptene. 3 heptene. That's the part that always has me a little bit confused, because some would say that you put the ene right here in the end. Others will say that you put the 3 specifically right here. Others would say that you put the 3 right here. Enters the IPAC name. In the same IPAC name, there's different ways, which can be a little bit frustrating, because if I were to type in 5 bromo, 3 methyl, 3 heptene, okay. So then for this, but if I were to type, oops, sorry, 5 bromo, 4 methyl hep 3 ene. We also get that as well. Well, this is 4 methyl. But as you can see here, there's into the PubChem, so that also uses the IUPAC naming. That's also a possibility. So with this though, considering that it's always very tricky, I'm gonna go with what it says over here, just because. So we have still 5 bromo, so everything else stayed the same. Methyl 3 heptene. 5 bromo, 3 methyl, 3 heptene. That also works too. If there's 2 double bonds for some reason, like here for example, I guess it would have 3 7 heptadiene. And that's where I guess have the issue with it, just because it would look a lot better if it was hep 3 7 diene. Because if I did that, hep 3 7 diene doesn't really exist. Because unfortunately the internet does not have every possible combination of it, but that is my little, I guess, caveat here in terms of different naming, because it can get a little bit wonky in terms of what exactly they want you to do. So it's important that you follow whatever your instructor gives, because even the IPAC naming specifically can vary a little bit within itself. So now, with that being said, let's go on to question number 20. We have, nice, how many cups in a quart? Okay. So, with that being said, let's look at our units. Maybe, yes, we have 1 liter is this amount of quarts, which is actually perfect, because all we need to do is know how many liters are in a cup. So first, we're going to start with a quart. So, and because we want to make sure this is translatable with everything, we have X quarts. Okay? And then we want to get that over to liters, because there is, for every liter, there is 1.057 quarts according to this conversion sheet. Alright, and so these units now cancel out. So now we're dealing with liters. How many liters, well, how many cups are in a liter? Cups in liter. So according to this, there are, for every liter, there's 4.22675 cups. So now we've canceled the liters and we're left with cups. So based on this, we have, it's going to be X divided by 1.057 times 4.22675. And around, we can round it up, because what we get actually is there's approximately 4x cups. So for every quart, so every 1 quart, there should be 4 times of that amount to be for the cups. So if we start out with, like, let's say 7 quarts, we would have 28 cups of whatever liquid. So let's see how we did. A fluid quart, there's 2 different measurements in the US and the UK. It looks like we're using, oh, and there's dry and fluid. So 4 cups we definitely got for the fluid, and then there's all these different conversions of dry, and then the UK, 1 quart UK is 4 cups UK. So usually it's just a 1-to-4 ratio typically. The key thing here, though, to understand is that, well, based on where you're residing and everything else, is that you want to make sure that whatever conversion sheet you're using is the one typically provided to you by your teacher, because, or in your textbook, because as you can see here, there's definitely different types, like even considering like whether it's dry versus whether you actually have fluid. These are all the things to consider, and because of that, you want to make sure that whatever you're trying to convert to, you're referring it from your textbook, because then you'll see that you don't want to have situations where you're using this conversion here, because what if you're working with liquids, and vice versa, if you're working with solids, you don't want to be using this here when you would actually be using the dry version. But this is really good. This is correct. And with that, that is it for question 20. And that is all we have for today. I just want to thank you again for joining me this stream. Just remember, if you want to elaborate more on any of the questions we covered today, or you want to just have some extra help with tutoring, definitely check out the links in the description below. With that, have a great rest of your night, and once again, thanks for joining me.